Hello everyone and welcome to our channel, Mootechie. It's so wonderful to have you with us today as we dive into a fascinating chemistry topic, salt hydrolysis. Get ready to unlock the secrets of why some salt solutions are neutral while others are surprisingly acidic or basic. Let's begin with the very definition. Salt hydrolysis is the reaction of the anions or cations in a salt with water to form an acidic or basic solution. Now, let's explore the central question. What happens when you mix a salt with water? The result can be one of three things: a neutral solution, a basic solution, or an acidic solution. Moving forward, we'll see a helpful table that breaks down the behavior of different salts in water. For a neutral salt solution, examples include sodium chloride, potassium bromide, and barium nitrate. These have a pH of 7.0. The nature of their ions involves a cation from a strong base, and no ion reacts with water. For acidic salt solutions, we have several categories. One type includes salts like ammonium chloride, ammonium nitrate, and methylammonium bromide, with a pH less than 7.0. Here, the anion comes from a strong acid, and it's the cation that reacts with water. Another type includes salts like aluminum nitrate, chromium chloride, and iron bromide, where the cation is from a weak base, and it's the cation that reacts. A final acidic category includes salts like sodium dihydrogen phosphate, potassium hydrogen sulfite, and sodium hydrogen sulfite. For basic salt solutions, examples are sodium acetate, potassium fluoride, and sodium carbonate, with a pH greater than 7.0. The nature of the ions can be the first anion of a polyprotic acid, a cation from a strong base, or an anion from a weak acid. In all these cases, it is the anion that reacts with water. Coming up, we'll discuss the first type in more detail, a neutral solution. This occurs when a salt is the conjugate of a strong acid and the conjugate of a strong base. A few things to consider. Metal hydroxides of group 1 and 2, except for beryllium, are strong bases. All other metal hydroxides are weak bases. The table here reinforces these points. For neutral solutions, salts like sodium chloride and potassium bromide are examples. For acidic solutions, we see ammonium chloride, aluminum nitrate, and sodium dihydrogen phosphate, among others. For basic solutions, we have sodium acetate and potassium fluoride. Now let's look at the second outcome, a basic solution. This happens when you have the conjugate of a weak acid and the conjugate of a strong base. The table appears again to summarize the same examples we saw before, like neutral sodium chloride, acidic ammonium chloride, and basic sodium acetate. To understand this better, let's examine a specific example, sodium ethanoate. This is the salt of a weak acid, acetic acid, and a strong base, sodium hydroxide. It completely ionizes in solution into acetate ions and sodium ions. The acetate ion then acts as a base in water, taking a proton from water. This reaction produces acetic acid and a hydroxide ion, and that is why the resulting solution is basic. Next, we explore the third outcome, an acidic solution. This results when you have the conjugate of a weak base and the conjugate of a strong acid. The table is shown once more for clarity, with its categories of neutral, acidic, and basic salt solutions. Let's look at another concrete example. Ammonium chloride. This salt comes from a strong acid, hydrochloric acid, and a weak base, ammonia. It ionizes completely into ammonium ions and chloride ions. The ammonium ion then acts as an acid in water, reacting to form hydronium ions and ammonia. This production of hydronium ions is exactly why the resulting solution is acidic. Now for a little question time to test our understanding. Determine if these aqueous solutions will be acidic, basic, or neutral. Ammonium nitrate, potassium chloride, sodium bicarbonate, and sodium sulfite. Pause for a moment and think about the rules we've learned. Let's now summarize with some general rules. When the negative ion is from a weak acid, then the salt is basic by hydrolysis. When the positive ion is from a weak base, then the salt is acidic by hydrolysis. If the salt is formed from a strong acid and a strong base, then it is neutral. And if the salt is formed from a weak acid and a weak base, then its hydrolysis is determined by the relative strength of the Ka and Kb values. Finally, let's touch on the concept of charge density. This effect is typified in aluminum salts. The aluminum ion has a charge of 3+, which is very high. This high charge density is why aluminum salts are so acidic in solution. Thank you. See you in the next class.